Hi everyone, welcome to this new video lecture of fluid mechanics. In this lecture, we'll discuss about the capillarity or capillary action, or we can say as a capillary motion, or we can also call it as a wicking. So this is the concept actually. It is the ability of a liquid to flow in a narrow space without any assistance of or even opposition to any external force like gravity. Or we can say it is the movement of a liquid through or along another material against an opposing force like gravity. Okay. So what is the meaning of this? Let's try to understand this concept. Suppose if you have taken a here one container of liquid is there, and this liquid actually what I have taken is a water. And in this liquid, if you pour a tube, glass tube in that, then we can see some kind of increment of this water level in this tube will be identified. Okay, and that is called actually the capillarity action. Okay, some examples also I have given, and one more example I'll give you. The same container, if I consider, let me draw a container here, and this container is full of suppose water is there, and in this container let me pour a small glass tube like this. Then we can see immediately some water particles will be, or water molecules will be rise this water tube, this in this glass tube. Okay, and this is one concept. And that in this glass tube we can see that water shape will be in the different way. In this way will be there. Okay, and similarly another tube, if I keep a big tube suppose, okay, but in this you can see that much rise will be not there. Okay, there will be rise, but it will be compared to the small tube. In the larger tube it will be very less rise in water will be there in this. Okay, so this is also one concept is there in this. Okay, so why it is happening? Due to the capillarity, means even gravity is there, still the water is able to rise in the glass tube. That is one concept. And some other examples also I have taken. If somewhere the tea or coffee falls, immediately we used to take a tissue paper and we used to clean that area. That means the tissue will be soaked this liquid part, that tea or coffee, immediately. So this concept also is coming under the capillarity. And one more example here I've taken. If you see, when you're pouring the water in a plants or any kind of small trees, then we used to give the water at this root level. Okay, you can see at this root level we used to provide this water, but from the root level to the top level or to the tree, that water will be provided, or the water will be passed like any like a pump is there, and it used to supply the water to that next end. So this is also due to the capillary motion or capillary action. Okay, and you know that most of the home they used to put this diya or agarbatti or the deep, and we used to pour some kind of ghees or oils in that, and there is a cotton is there, and we think that the cotton is burning, but ultimately it is not like that. The oil actually burning through this medium as a cotton. So you can see that if you keep the diya like this, and if you pour full of oil in that, you can see though it is burning, the cotton is burning, but with the help of this liquid only, in the help of this ghee or oil only, it is burning. So how it is happening? Here also due to the action of this capillarity. That means that cotton is soaking this oil and it is burning here. Okay, similarly this is another one example, and this is one more example what I have given in the drug delivery to our health or to our body. Okay, there also capillary action is also working. And similarly, if you take two containers and with the help of some cottons, okay, we can pour the water or pour the liquids from one container to the other container. So that is also one concept of capillarity. Okay, so this capillary actually maybe capillary rise will be there or maybe fall will be there. Due to this, when you're pouring the putting this tube inside the liquid may rise or liquid may fall. It depends on the what kind of liquid you have taken. Okay, so there is a two chances are there. capillary rise or capillary fall. So first we'll see the expression for the capillary rise. So here the example I have, that diagram I have taken. So there is a liquid is there that is called, I already told, water. And if you pour it glass tube inside that, you can see there is a rise in water is there in this. And how much rise is there? That is actually H. That is denoted in H. And this kind of shape will be identified for the rise in water. It's very small. It will be difficult to identify in that normal eyes, but you can take a microscope also. You can see that this kind of curve will be visible at the top layer of the tube. Okay, and here if you see the action that surface tension is acting on this this surface. Okay, and if you draw this surface tension, so that will be acting tangentially to this, and let's see, write this is sigma to that. Okay, and the angle made between this glass surface and this curve, that is theta. Okay, so the expression for the rise, capillary rise, actually it used to happen for the two reasons. So first one is that we can say due to the surface tensile force. Okay, so that is nothing but sigma. Okay, due to the surface tensile force, and another one is the weight of the liquid. That means how much water was inside the tube. So that is we can say W. So weight of the liquid, W. So that we can write weight of the liquid, what we know, W equal to mg. Okay, and m equal to, we know that density equal to mass by volume. So we can write here m, mass of the liquid, equal to density into volume. So here also I can write rho, v and g, density, volume and gravity. Okay, so density, we know density of the liquid, and volume is what area and what height was increased in this tube. How much area is there, what is the height increase. So that is nothing but volume. You can write rho into area. Area means that glass tube area, pi by 4 d square, and what is the height was increased, h into g. So that this is your weight of the liquid, okay, which is in the content. And this is, we can write rho pi by 4 d square into gh. Okay, so this is weight of the liquid. And another one is there, that is the surface tensile force. As I told you, surface tensile force which is acting here. So that is this sigma. Okay, that actually what we can write, this surface tensile force, let me write here the tensile force which is acting here, that is actually how to, this equal to surface tensile force equal to this sigma which is acting here. So we need to take the forces in vertically downward and upward direction, because we have taken this vertical tube here. Okay, so the sigma will be act in this direction with an angle. Now if I resolve in the y components, okay, so that will be sigma cos theta. So that will be sigma cos theta. Okay, and so what is the tensile force will be there? So the tensile force is nothing but, we can write this sigma cos theta into the circumference, Okay, that means the surface tensile force acting on which area, at that what zone it is acting. So circumference of the tube. So that we can write surface tensile force, what is acting here. See what we have taken first one, the weight of the body. So weight of the liquid which is vertically downward direction, and here the sigma which is acting, we need to take in the opposite direction, that one in the y direction. So that we can take in this. So both will be equilibrium there. So this one we can write tensile force equal to sigma cos theta, into the circumference. Circumference is nothing but, here we know that pi d. Okay, circumference is pi d. So now two things we got. One is surface tensile force, one is weight of the liquid. So this is one equation and this is another equation, suppose. Now to make it in equilibrium condition, let compare these two equations. So equation 1 and equation 2. So let equalize to, so that is rho pi by 4 d square and gh equal to, and this is here sigma cos theta into pi d. Okay, sigma cos theta into pi d. So what actually we need to identify? We need to identify what is the height raised here. What is the height of the liquid which is raised inside the tube? So what I'll do, I'll keep this h one side. Which one? This h, well, I'll keep one side. Remaining terms I'll take it to other side. So here pi d, you can see pi d, here pi d will be cancelled, and here one d will be there. Okay, so h equal to, I can get here, this 4 will come this side, so that will be 4 sigma cos theta, 4 sigma cos theta divided by, you can say, this rho gh, so already h here there, so you can write rho g, and one more d will be there, so that will become again down d. So this is the formula for this. What the, how much height was increased in this? So that is equal to, so I can say here, this is the formula, h equal to 4 sigma cos theta by rho gd. Okay, now here the theta, actually what we have taken, this angle between the surface and this liquid. So that sometimes, you know, very small will be there. In that case, we used to consider the theta equal to 0 degree. That's theta equal to 0 degree. Then cos 0 will be 1. So you can write that is 4 sigma divided by rho gd. Okay, so this will be the equation for this, for capillary rise. Okay, similarly we'll see the capillary fall. In the capillary fall, if you see, let me take another one. Yeah, in the capillary fall, if you see, again here the liquid is different. Previously we have taken the liquid as water. Now here we need to consider this liquid as a mercury. Okay, now if you consider a container here, again inside the container, again we need to put some liquid here, and that liquid will be different than the others, than the previous one what we have taken. Okay, so previously we have taken water, and here we will consider mercury. So in the previous case, what we have seen, there is a rise in liquid here. Okay, why? Because the intermolecular forces between this water is very less than the surface what we are providing here. Okay, so due to that, the liquid rises here. And while coming to this capillary fall, if you see, now while putting this glass tube inside this mercury, we can see there is no rise in liquid in this tube, rather than the liquid falls. Okay, the liquid fall down here. So why this is fall down? Because due to the intermolecular forces between the mercury. Okay, it is very strong, and it won't allows the external substances to enter inside that. That's why it used to go inside without on behalf of rising, it falls. Okay, and so for this also one expression is there, like some derivation is there, expression for the capillary fall. Okay, so for this we can see here the surface tension, the sigma which is acting here, and in this we can see there is a pressure acting here. Okay, this is actually hydrostatic pressure which is acting here and is trying to go up, and the theta which is acting here between this glass surface and this tangent of the liquid, that is sigma. Okay, so these two things are acting here. Now here also again we need to identify, and this is the height from this liquid surface, how much down, how much fall happened in this liquid. So for this also we can write the expression for the capillary fall. Again here also again two concepts will be there. One is surface tensile force. So this capillary fall happen, and what are the effects will be there in this capillary fall? Now first one is the surface tension acting, okay, and acting, this is downward, acting downward direction, the surface tension acting downward direction. Okay, so that one how much you can write? So similarly here also you can write surface tension which is acting downward, that is sigma, and you can resolve this in terms of downward direction, y direction. Okay, so this will get here again sigma cos theta. So sigma cos theta into surface tension, we can write that circumference. What is the circumference of this? So that is nothing but pi d. So sigma cos theta into pi d. So this is one effect. Another effect is that, as I told you, due to the hydrostatic law, there is a pressure, the intensity of pressure actually. So that is nothing but that intensity of pressure which is acting on this. Okay, and due to the hydrostatic force, the acting upward direction, and this intensity of pressure will be there, and due to this this effect will be vertically upward. Okay, and that one we can write intensity of pressure, we can write, or intensity of, that means the force equal to, we can write P into area, pressure into area. We know that pressure equal to force by area. So force we can write intensity of force, or we can write pressure into area. So here P equal to, we know that rho GH, P equal to rho GH into area equal to what? Pi by 4 d square. Area equal to pi by 4 d square. So now this is equation 2. Now again, because we know that we need to equilibrium of these two equations. So compare this equation 1 and 2. What we can get? Sigma cos theta into pi d equal to, again, rho GH pi by 4 d square. This is nothing but the similar kind of equation what we got in the previously. So pi d, here pi d will be cancelled. So actually what we need to calculate, we need to identify the how much fall happened here. So H will keep, I'll keep one side, remaining term I will take other side. Now this 4 will take it here. So 4 sigma cos theta, and here what is there? Rho g d. So rho g, so d. So this is also similar equation what we got previously. Let me show you here. Here see H equal to 4 sigma cos theta rho g d. So here also we got H equal to 4 sigma cos theta by rho g d. Now here the theta will be actually 128 degree, because the mercury, you can see the angle between these two, this glass surface and this tangential surface tensile force. So this is 128 degree. Remaining all the things same. And this is all the things happening due to the cohesive things and adhesive. So this cohesive and adhesive terms we already discussed in the previous lecture. If you are having any doubt, you can see in the previous lecture. Now one more diagram I have shown you, the diameter and with respect to height of the tube. So what is the relation between these two? Okay. Now the diameter of the tube, if you see, if I decrease the diameter of the tube and that increase in diameter of the tube, this one is going to diameter of the tube, and this is the height. Okay, as I told previously, I have shown you that if I am increasing the diameter of this, the height is also decreasing. Now see, this is the same thing happening here. Okay, so I hope you understood all the things. If you are having doubt, you can give a comment in the comment box. Thank you all.